All right, let's review some of the main concepts we've seen in our course so far. So the first thing we did in our course was look at the Taylor polynomials for your function f at a given value a. And what we found was that Taylor polynomial y can be expressed this way. So here's our sum. You take a bunch of derivatives, you divide by k factorial, and you can get a polynomial that's a very good approximation to your function near a. This is the best possible degree n polynomial that can fit your function at the value a. So then the question is, how good of an approximation is it? If I plug in a number c that's really close to a into my Taylor polynomial, how far away am I from the actual value of the function? So that's what this 2 property says. Item 2 on my list says the difference between the actual value of your function at c and what you get when you plug in c to this approximation is less than or equal to this quantity. This is an error bound. It tells you how far off you could actually be. The value m satisfies some property. So we did a bunch of examples with the error bound for general Taylor polynomials. Then we thought, well, what would happen if this n was infinity? What if you never stopped writing down terms? Instead of having a degree n polynomial, what would it look like if you had a Taylor series? So this is the Taylor polynomial where the terms are arbitrarily large. We've seen examples of Taylor series. Here are my top 3. You got to know these. E to the x, the geometric series 1 over 1 minus x, and sine x. The radius of convergence tells you the values of x that you could actually plug in to get an equality. So a radius of convergence infinity means every value of x can be plugged in here to get a good equation. R equals 1 means only x values in between -1 and 1 give you equality. Other than that, the series diverges. And here, the radius of convergence for sine x is infinity. How do you find these radius of convergence? How do you decide if a series converges or not? That's when we talked about all of our convergence tests. So we had a bunch of convergence tests, a bunch of ways to see if your series converges. First of all, you could see if you have a geometric series. If you just have something of the form x to the n power. That's a geometric series. You might have a p series. That's when you had something of the form 1 over n to the p. There's the integral test where you can compare your series to an integral and see if that converges. Then we have the direct comparison test, the limit comparison test, root test, ratio test, and then if you happen to be lucky enough to get an alternating series, that's my favorite. It's easy to see if an alternating series converges because the terms just have to go to 0. And if you happen to have an alternating series, it's easy to approximate your series with a finite sum. The error of an alternating series when you approximate with a finite sum is less than the next term you would have written down in the series. And then lastly, the last topic that we had was the observation that series can be differentiated, they can be integrated, they can be multiplied, you could take limits. Any operation you could do in calculus on a function, you could do with a series, most likely in an easier way. This is kind of the point of the whole first part of the course. The idea is you take a function, you turn it into a series, and the series is usually easier to deal with than the function itself. So you could take derivatives easier, you can integrate series just by integrating term by term when sometimes you can't even integrate the function itself. Okay, I'd like to do the next few videos with examples of questions you might see on the first midterm.